Okay, so we are gonna touch about this example of segregation. And basically this is using a simple model of segregation index, calculate the segregation index for account some segregation. So this is basically a kind of a background, what we discussed about segregation. So as you know, basically when a material solidified in the first trunk of dendrites, and the second dendrites are the ones that are forming, according with the theory, the segregation in interdendritic regions. So this is kind of a profile of how the segregation could look like. So we have a composition, like the standard, the base composition of the steel, in this case C0, the material. We have a higher level of segregation in the interdendritic regions and the lean regions inside the secondary dendrites. So this model can be mathematically described by this equation. Like as you see, it's like a really complex equation, like describing this type of sequence wave or profile. So you can just use this equation for solving the segregation, but obviously there are a lot of terms here that are sometimes difficult to handle. So there are some tricks in metallurgy that we can use for calculating easier the segregation. In this case, we are gonna see an example of the segregation index. Basically, this segregation index L delta is expressed as using this equation. Basically, is the change in composition, as you see here, the composition on time, based in the base composition, the base composition and the maximum composition that is in the interdendritic region. So this composition is going to change according with experimental exponential formula, sorry. And this exponential equation is in terms of the diffusivity of the material. In this case, the diffusivity depends, remember, of the activation energy and the temperature as described in this equation. So if we put the diffusivity here for a particular temperature, for a particular composition, and if we know the secondary arms space, we can determine this delta. And this delta is going to tell us, this delta first is a function to go from 1 to 0. And if this delta is 1, it means 0, or the material hasn't segregated at all, so we have maximum segregation. If this number goes to close to 0, basically it means that the material is approaching the base composition. So in this curve example here, you'll see like the base composition is Z0, in this case. Due to the segregation, we have a maximum composition in the interdendritic region, and this is the profile that we have. And we are just plotting like a half of the interdendritic arm spacing, just to assume that this is the dendrite and this is in the middle of this is the interdendritic region and this is in the middle of the dendrite. So after some time using this index, we are gonna go to, this number is gonna approach to 0. So basically this profile is approaching to C sub 0. In this slide, we saw like some examples of how the micros looks like. So in this case, for a copper aluminum alloy at 700, that has been homogenized at 700 for different hours. And as you see, basically at a short time, we have dendrites that basically we can assume here that in the interdendritic region is around 100 micros. And after 12 hours, 24 hours, seems that the dendrite is disappearing. And obviously after 24 hours, it's mostly gone. So we can quantify that using that index, and this is the example that we want to see in how to calculate using MATLAB in our case. So it's based in that alloy that I just showed you. So first we need to calculate the diffusivity, and the diffusivity for this particular system at 700, we need to use a Q of 45 calories per mole. That's the units, and this sub 0, which is this exponent, is going to be 0.39 centimeters squared per second. Now, if we calculate this diffusivity for 700, and remember the temperature should be in Fahrenheit, we can obtain diffusivity of this value, really a small value. And after that, we can place this diffusivity in our equation to calculate the index. And using different interdendritic arm spaces, in our case, due to the microstructure we saw, it's around 100, but we are also going to compare with 200. We can plot that, and at different times, so T here is time, at the time, we can observe the evolution of this index. So in this plot, basically what I'm showing you is 1 minus the number of index, which is going to explain us what level of segregation we have in each level. So let's jump to MATLAB. In this case, this is the code that I'm sharing, something that I can share, and I also place in Canvas. So this is just a description. So we have the constant of the gases, temperature at 700. Here is changing to Kelvin. The activation energy that we said that is in calories per mole. So we need to change it to joules per mole. It's international units. In this case, we can change everything to international units. So we're multiplying for these factors. So we have the units. And in this case, d sub 0 is in centimeters squared per second. So we can multiply using this equation, all of the terms, and we're going to obtain, after running this part of the code, we are going to obtain the value of 2.44. So after running here, we have the 2.44 at the power of minus 11. So that's the d0. Now, just now consider that this is going to have the same units of the diffusivity. So it's centimeters squared per second. So that diffusivity has that unit, centimeters squared per second, because it's the same units of the diffusivity coefficient. Now, we want to see in terms of time at different times. So in this case, time must be in seconds for this equation. So that's what I'm putting here, a time vector for hour, but in seconds. So it goes from 0 to 48 hours, but I multiply by 3600 to account for seconds. So in this case, the time vector that goes from different values, 1 to 48 hours, but in seconds. And here I'm having like the secondary arm spacing. So I assuming 100 and 200 according to the example. But remember, the units needs to be in centimeters. So I'm changing here to centimeters, the secondary arm spacing to the power of minus 4. Now I can apply the equation. So we have two different deltas or segregation index. So the first one is counting 100 micros and the second is counting 200 micros. So here is the calculation. And after that, in MATLAB, I can plot this in this curve. So I have the first figure is plotting time in hours. So I divide it by 1300. And delta, in this case, this is the blue curve. And after that, the same plot, but delta 2, in this case, this one. So we have the index 1 and the index 2. So you see basically the index 1, the first index, when 100 micros, it's the index is moving much faster. In 24 hours, basically, is going to 0.8. You know, I can just plot in the just go in the plot and select this point, for example, and it's gonna tell me that is around 18.18. So basically, you know, 1 minus that is gonna give me around 82% segregation, right? It's a reduce of segregation. In the case of the 200, after 48 hours, I can see that is 65 or 66 approximately. So 1 minus that, it's 34, right? So we have in this case 34 segregation. So that's basically what the table is telling us, the table that I was sharing before. So basically from here we can extract the different times, the different index at different times, and with that we can calculate the values that I was showing here in this table. So after 84 hours, for example, the index was in around 18 point something, right? 18.9, so 19 basically. This index is almost 19, right? 0.19. So 1 minus that is 81. So basically the segregation had reduced 81%. In the case of the 88 hours, this interdendritic arm spacing, we have 66. So the reduction is going to be 34. Yeah, sorry, 34. So we can do the same for the different times to account for the level of segregation. So notice that even though that it was hard to see in the micro, according with these calculations, theoretical calculations, we still have, we have reduced significantly the segregation for this particular case of 100 micros, but it's still not completely, homogeneous. So basically, what it's telling us is that the homogenization takes a long time for these systems. So that's the example that I wanted to share. Also, here in MATLAB, the other thing that you could do is extract directly the vectors if you don't want to read directly in the plot. Because you have delta and delta 2, you can go directly to MATLAB, and in the workspace, there are going to be the two deltas that you calculated. So here are the vectors of deltas. And the vector of time basically is in seconds. So this is counts 1 hour, 2 hours, 3 hours. If you divide this time by 1300, it's going to give you in hours. So for example, if I say time in hours, it's going to be time divided by 360. So now this TH is the time in hours, the same vector, but in hours. So we have 1, 2, 3, 4. So for example, in 6 hours is the column 7. If I come to delta, column 7, we have 81% this index. And for the case 2, we have 94, 95%, in this case, 90.95, which basically is the data that I can extract from this plot, but here you can see the vectors numerically. So that's the example that I wanted to share, and that's how we calculate using the segregation index, the level of segregation in different metals.